In this section, we are going to study the convections, one of the methods to transfer the energy from inside to the outside in the stars. When we study the Eddington luminosities, we obtained this relation. Round P sub large over round P is the total pressure is equal to kappa F over 4 pi CGM. Have to be the less than 1. So in this case, energy is transferred by radiations. So from these equations, we could find this is exactly equal to this one. Kappa F is smaller than the 4 pi C GM. This could be violated for the kappa becomes large or when the F is really large ones. So high F or high kappa, this condition cannot be satisfied. So steep temperature gradient we could expect. Then instead of energy transfer by radiations, convection is responsible for energy transfer in the stars. Convection transfers energy and mixes the materials. Then we'd like to consider the onset of convection after the Schwarzschild in 1906. Some element of gas moving upward. In this region, the density and pressures of the gas element is expressed rho sub 1 and p sub 1. Gas element is moving upward, and in these regions, density and pressures of the gas is expressed rho sub 2 and p sub 2. So suppose the element moves a small distance outward. The element expands until the internal and external pressures are in balance. There is no heat exchange between the inside of the element and outside of the element. Dynamical equilibrium is easily maintained, so pressure becomes equal. So P sub star is equal to the P sub 2. During the motions of the gas element is moving upward, pressure and density is changing from the rho sub 1 to the rho sub stars. And the pressure is changing P sub 1 to the P sub stars. Dynamical equilibrium is maintained quickly. So pressures P sub 2 and P sub stars have to become exactly equal in the short time scale. Then density cannot become same. So there are two possibilities. If the rho sub stars is larger than the rho sub 2, so density of this element is larger than the density in the surrounding areas, this element is sinking to the original positions. So in this situation, state becomes stable. We have a stable state. But if the rho sub star is smaller than the rho sub 2, the element is keep moving upward. This is correspond to the unstable mode. We call the convections. Condition for the stabilities. So adiabatic curve is expressed. P is proportional to the rho to the gamma. So if you express round P, round rho is going to gamma K, rho gamma minus 1. So this is gamma P over rho. So in adiabatic, round P, round rho is equal to the gamma times P over rho. When the hypothetical stellar structures is expressed the green ones, then you could compare the density at these 2 points. So gas element is start moving this point rho sub 1 and P sub 1, and following the adiabatic curves and come to this point. In this situation, rho sub star is larger than rho sub 2. So in this case, gas element is sinking to the original positions. This is stable case. When we consider the hypothetical stellar structure expressed the red curves, then density is rho sub 2 is larger than rho sub stars. So in this situation, rho sub star is less than rho sub 2. So this gas element is keep moving upward. This corresponds to the convection. This is unstable mode. So the condition for the stabilities is expressed. So if the slope is shallower than the adiabatic slope, condition for stabilities. So you can substitute. This is round P, round rho. Star is less than the round P, round rho, adiabatic. So this is equal to, you can substitute this here, gamma P over rho. So you can express this is rho over P, round rho. Star is less than the gamma. So if you use a log, this is log P over round log rho stars is less than the gamma. This is a condition for the stabilities. Then convections. Convection energy transport takes place when radiative transfer equation is no longer valid. Energy transport equation should be replaced by another equation that takes into account the convections. In convective zones, departure from the adiabaticity is very small. I'd like to show you. So inside of the stars, in the convective zones, we expect pressures as a function of the density. It should be expressed following this equation. So we consider convective cell inside of a stars. So mass of the convective cell is m sub c, and thickness is r sub c. This is r sub c inside of the shell, m sub c, and the energy flux inside inner boundary of the shell per unit time is F. Then energy is absorbed in the convective shell that acquires a surplus temperature delta T over the temperature T of its surrounding. Delta T over T is a measure of the super adiabaticity. So super adiabaticity, so we'd like to study. Then delta P should be 0. Mass element is in dynamical equilibrium with its surrounding. So delta P is 0. We could consider the equation of state. P equals rho kt over mu m sub h. So this means log P equals log rho plus log T plus constant log K over mu mh. Then take a small change the both sides. So this means delta P over P over delta rho over rho plus delta T over T. If the delta P is 0, then delta rho over rho is equal to minus delta T over T. With an increase in the temperature, so delta T is positive, then density decreases because the delta rho is a negative values. So gas element start move upward. So this is the onset of the convections. So density deficit is related with the delta T over T. So amount of the energy absorbed in the shell is F times the RC over VC. This is the time for the energy is passing through the convecting cell. So if you multiply the flux, energy flux times is the amount of the energy absorbed in the shell. Relative rise in the temperature is the absorbed energy divided the total amount of the internal energy. Is a U times M sub C. Then we could estimate the relative rise in temperatures. If you write under R sub C over V sub C is expressed 1 over square root Gm over R squared delta rho over rho 1 over RC. Then this part exactly equals to delta T over T. Delta T over T squares equal F squares over U M sub C squares 1 over Gm over R squares delta T over T 1 over R sub C. So from these equations we have a delta T is here. So delta T over T cube equal F squares over U M sub C squares 1 over Gm over R squares R sub C. Have this relation. Then from these equations you can substitute flux order of estimate. Flux is luminosities and UMC is the total internal energies of stars, and R and R sub C both equal to the radius of stars. Then we have these equations, and U over L is the thermal time scale, and 1 over square root Gm over R cube. This is dynamical time scale. So delta T over T is expressed the ratio of the dynamical time scale over the thermal time scale. So if we substitute the quantity we estimate, we could find the 10 to minus 8. So temperature gradient is very close to the adiabatics inside of the stars when the convection is responsible for the energy transport. Okay, this is the end of this session.